Hi students, let's look at topic 13 on solubility equilibrium. This is a shift away from the 3 or 4 organic chemistry topic we had. So I think solubility equilibrium is a pretty nice topic to end the year with because I think number one, it's kind of straightforward, and number two, you can use the concepts which you have studied under chemical equilibrium to help you understand most of it. In fact, if you truly understand Le Chatelier's principle and you are able to appreciate how the position of equilibrium will shift given the access or the introduction of reactants at the product or reactant sites, then I think it's quite easy for you to understand solubility equilibrium. And another aspect of this would be the fact that you are currently doing the dry practical for QA. So it's very good. In fact, it's very intuitive for you to have solubility equilibrium side by side so that you will be able to appreciate, for example, when I introduce let's say, soda hydroxide to a solution containing copper 2, why is it that I observe blue precipitates coming out? Yeah, so after you learn solubility equilibrium, then you will be able to appreciate ideas such as because at the introduction of hydroxide, at that point, the ionic product, which of course at this stage you will not be able to appreciate what is ionic product, but you will be able to tell that, okay, so this particular product of the multiplication between the instantaneous concentration of OH minus and then raised to the power of 2 in this case, with copper 2, when you multiply them together at that instance with the introduction of OH minus, you will realize that it actually exceeds the Ksp, okay, of copper 2 hydroxide, which results in the precipitation of blue PBT of copper 2 hydroxide. Yeah, so you will be able to appreciate such precipitation a little bit better as compared to in secondary school, when you're simply just adding sodium hydroxide to all the unknown cations and then you just take note of the color. And of course, having a good understanding of solubility equilibrium, you will be able to explore such as why is it that when I add excess of some reagents, for example, aqueous ammonia to copper 2 hydroxides, and let's say sodium hydroxide to excess sodium hydroxide to aluminum hydroxide precipitate, you will be able to dissolve in excess. So I think having a good understanding of solubility equilibrium allows you to explore some of these concepts a little bit better. You will be able to have a clearer understanding, a clearer picture. Okay, so if you take a look at the learning outcomes, actually there are just 3. You're supposed to show understanding and apply the concept of solubility products, which is shown by Ksp. Solubility products is actually the equilibrium constant. Okay, in case you're still not familiar about this topic. Yeah, so it's actually the equilibrium constant known as Ksp, and later on we'll be introducing you to that. And you might want to revise a little bit on chemical equilibrium before tackling this topic, because whatever applies in chemical equilibrium applies to this topic as well. So that means that you need to be aware that equilibrium constant is a temperature dependent variable. Yeah. So therefore Ksp value will change according to temperature. Yeah, but the value of Ksp will remain a constant regardless of any combination of anions and cations or even the salts in the system. I think we need to have this particular understanding. And then we have a objective 10.2b is solely a mathematical objective, like how do you calculate Ksp from the concentration and vice versa. So we'll work through that. And then 10.2c, you will be introduced to a term known as the common ion effect, and of course the formation of complex ions as exemplified by halides with aqueous silver ions. Yeah, so this is probably something which you need to take note of, because you will need to be familiar with this for your practicals. Okay, yeah, so without further ado, we'll just jump straight in. Okay, so as I mentioned, this topic is related to chemical equilibrium. So if you have forgotten about the ideas of chemical equilibrium, it will be good for you to review your notes, or you can watch an earlier video which was created for chemical equilibrium. Other than that, if you are familiar, then it's not really a big issue. You can just jump straight in. Okay, but we have to be familiar that, or we have to be aware that for solubility equilibrium, it's actually related to a heterogeneous system. Yeah, so for example, I have a solid. So let's say Mx, which is a solid, or rather it's a salt. So this particular salt, despite being insoluble, it's actually able to maintain a small concentration of the cation. So in this case, we assume that the charge is +1, and a small concentration of the anion um, at a given temperature. Yeah, so we say that although the solubility is very low, let's say the solubility is A. So at equilibrium, I will have A moles of M plus and A moles of X minus. Yeah, so if you are able to come to terms with this particular idea, and the fact that what you are going to get in the solution is actually a saturated solution, then you actually don't really need to go through a lot in details of this topic, because you already have the basic sense of this idea known as solubility equilibrium. Okay, yeah, so I think we'll just jump straight in. So first of all, we need to introduce you to the term solubility and saturated solution. Yeah, so we have to be aware that the solubility of a salt actually is determined by the amount of the solutes that can be dissolved in 1 dm cube of a given solvent. Usually the given solvent is water. Yeah, so if it's indicated to be other things, I think it will be indicated somewhere in the table or in the information. Okay, and usually solubility is quoted either in terms of moles per dm cube, or in terms of grams per dm cube of the solvent, of course. Yeah. If it's ambiguous, then the question usually will tell you, is it in moles per dm cube or grams per dm cube? If the question didn't tell you, then you can assume that it should be in terms of moles per dm cube. Okay, so in this case, sodium chloride is very soluble in water. So the solubility is 357 grams per dm cube, or in terms of moles will be 6.102 moles per dm cube. So what this means is that it cannot dissolve beyond 357 grams of sodium chloride in 1 dm cube of water. So if I add a bit more, then you will start to see precipitate coming out. Yeah, so in some sense, when we dissolve the maximum amount of the salt in the given solvent, we have already formed what we call a saturated solution. I think this is an idea which you should be familiar with from what you have done in secondary school. Okay, a saturated solution. So a saturated solution is formed when I can't dissolve any more solutes. Okay, yeah. So in particular, for the topic on solubility equilibrium, we are focusing our attention on ionic compounds. Okay, so for ionic compounds with low solubility, they are said to be sparingly soluble. Okay, so usually solubility products, we are concerned with salts that are sparingly soluble, or what we traditionally term as insoluble salt. Okay, so I'm sure in secondary school you'll be aware of a table like this, or your teacher will have told you things like, oh, all nitrates are soluble. Okay, all halides are soluble except silver, lead, or maybe mercury, if a teacher did tell you. And then all sulfates are soluble except lead sulfate, barium sulfate, and calcium sulfate. Yeah, so basically you learn about these solubility rules, or you're supposed to memorize some of these rules, maybe without actually understanding the mathematics behind, or without having an appreciation just beyond knowing that they are insoluble. Okay, so we introduce you to solubility products, basically just give you a short glimpse of something which you could probably understand a bit more. You are able to do a bit of calculation and link it to chemical equilibrium. So hopefully you have a more fruitful understanding of this topic. Okay, yep. So we have covered the saturated solution, so I don't think we'll go there. So we'll just jump straight into the third section on solubility equilibrium and solubility products. Okay, so yes, we are using the same example. So if we have an insoluble salt MX, no matter how insoluble it is still able to dissolve to a very small extent. So assume that a very small amount dissolved. So we have M plus and X minus. Okay, so in this case, we use silver chloride as an example. So silver chloride solid, insoluble, but it's able to maintain a small amount of silver plus aqueous and chloride aqueous. Yeah, so if we attempt to write an equilibrium constant Kc, which if you try to remember from chemical equilibrium, it should look something like this. Okay, what is going to happen is that you will notice that the concentration of a solid is actually a constant. Okay, why is it a constant? Because the density, essentially the concentration of a solid is its density, okay, in terms of moles per dm cube. Okay, of course density, it can be in terms of grams per dm cube, it's because it's the mass per unit volume. Yeah, but in this case, concentration of a solid is taken to be a constant because a solid has a fixed density. Yeah, so therefore when we shift the AgCl so-called concentration over to the left-hand side, we actually get a constant, we get a new equilibrium constant, and we term this as Ksp. Okay, so it's a capital K. Of course, you can't write it with italics, so it's a capital K with a subscript Sp. Yeah, so this represents solubility products of silver chloride. Okay, so take note of the units. So the units will be mole squared dm to the power minus 6 because it is derived from two concentration terms multiplying together. Okay, so with that, we have a definition over here. So the solubility product Ksp of a sparingly soluble salt is the product of the molar concentrations of the constituent ions in a saturated solution raised to the appropriate power at a given temperature. So the appropriate power being raised is linked to the stoichiometric coefficient. Okay, so please be aware of this. And please note that the solubility product concept is only applicable for sparingly soluble salts. Okay, if the salt is soluble, then it is not applicable. Why is that the case? I think it's beyond the scope of the curriculum. If you wish to, you can read a little bit more about that. But do take note that for most of such concept, it will only be applicable if you are looking at dilute solution. Yeah, which I think if you really wish to, you can actually explore more advanced text on this. Okay, yeah. So Ksp is usually a very small value. So you can take it that it is smaller than 10 to the power minus 4. Can be as low as 10 to the power minus 40. Okay, so as we mentioned at the start, Ksp is a temperature dependent variable because it's an equilibrium constant. Okay, yeah, and then there isn't a need for you to memorize this because you can always derive it from the given equation. Okay, so please do not attempt to memorize this. Okay, so the next thing we're going to do is we're going to write an expression for the solubility products for each of the following salts stating its units. So we're going to do this for exercise 3.1. So we'll do it for PBI2 first. Okay, so for PBI2, I don't think we need to write equation because you know that there are two equivalent of iodide for every one equivalent of lead iodide dissolving. So therefore, when we write out the solubility product, it will be Ksp equals to the concentration of lead 2 plus raised to the power 1, and then the concentration of iodide raised to the power of 2. Okay, so the same case for silver carbonate. So in this case, the Ksp will simply be the concentration of silver plus raised to the power of 2, and the concentration of carbonate raised to the power of 1. Okay, and then for calcium phosphate, we're going to do the same thing, Ksp. So that will be the concentration of calcium 2 plus raised to the power of 3. Okay, because one equivalent of calcium phosphate gives you 3 equivalents of calcium 2 plus and 2 equivalents of phosphate anions. So for phosphate concentration, it will be raised to the power of 2. Okay, then right now when we write the units, so in this case the units will be concentration multiplied by concentration raised to the power of 2. So that would be mole to the power of 3, and then dm to the power minus 9. Okay, or in short, just moles per dm cube raised to the power of 3. If that's easier for you. So in this case, we have 2 here, 1 here, so the units will be the same, mole to the power of 3, dm to the power minus 9. Okay, in this case, we have 3 plus 2, 5, so it will be mole to the power of 5, dm to the power minus 15. Okay, so I hope this is straightforward enough for you. Okay, then next, write an expression for the solubility products for each of the following sorts, stating the units. So it's the same thing. So again, the Ksp of iron carbonate will be equals to concentration of Fe2 plus raised to the power 1, and then concentration of carbonates raised to the power 1 as well. Okay, then of course the units will be mole per dm cube squared, so that will be mole squared dm minus 6. Okay, and then for strontium fluoride, in this case the Ksp will be equals to strontium 2 plus raised to the power 1, fluoride raised to the power of 2, units will be moles per dm cube raised to the power of 3, so that will be moles cubed dm minus 9. Okay, and then for mercury sulfate, the Ksp will be equals to, in this case for mercury, it will be Hg plus squared, and then for sulfate will be SO42 minus raised to the power 1. Units is the same thing, moles per dm cube raised to the power of 3, so moles to the power of 3 dm raised to the power minus 9. Okay, yeah, so that's it for exercise 3.2. We can move on to this particular table, and in experimental investigation on the solubility products of silver bromate at 16 degrees Celsius. Yeah, so these are values being obtained from experiments done at 16 degrees Celsius. So let's just try to look at the table, look at the information, and we see what kind of information we can get out from here. Okay, so we have different volumes of silver nitrate and potassium bromate, both at an initial concentration of 0.1 moles per dm cube. They were added to 200 cubic centimeters of distilled water at 16 degrees Celsius. Okay, so after that, the concentration of silver plus and bromate at equilibrium were determined and shown in the table below. Okay, so you notice that this is quite similar to what you have seen in kinetics experiment, but this is not kinetics. Okay, so please don't mix them up. Yeah, basically for this whole business, right, we are just trying to vary the volume of silver nitrate and potassium bromate, and we keep the total volume of both a constant at 50. Yeah, so you realize that the volume of silver nitrate goes down from 40 to 10, and then the volume of potassium bromate goes up from 10 to 40. Okay, so that's about it. This is not a kinetics experiment. Okay, because at the end of the day, I just want to ensure that when you look at the table, right, you know what's going on. Yeah, then you would expect that when you add the two solutions together, right, there will be one which is in excess. Yeah. Okay. So in this case, obviously you would expect silver plus to be in excess for the first one, or maybe for the first two. Yeah. Actually, at the end of the day, it doesn't really matter which is in excess, because you can actually do, or you can use some method to determine the amount or the concentration of silver plus and bromate at equilibrium, which was what was given to you over at this table. Yeah, so the scientists actually realized that, oh, okay, so for the first experiment, the concentration of silver plus at equilibrium, right, was found to be 0.0144, and then the concentration of bromate was found to be 0.024. Yeah, so remember that these are concentration of the respective ions dissolved in the solution. So which means the rest of the silver bromate has already been precipitated out. Yeah. So what the scientists did was just to multiply these two together, because when you multiply them together, technically you are defining Ksp. Okay, so the scientists got this value, 3.45 times 10 to the power minus 5. Yeah. So using the same method and mixing different volumes together, so altogether we have 5 experiments. So you notice that when you multiply the equilibrium concentration of silver plus and the equilibrium concentration of bromates together, right, this value is relatively constant. Of course, it varies a little bit because of experimental error, but I think the point we are trying to say is that the amount of silver plus, or the concentration of silver plus and bromate at equilibrium can vary, but when you multiply the two together, the value will be fixed, and this is what we call Ksp. Yeah, this is a very important idea, because some students have an impression that the amount of the insoluble salts in the system, in terms of cations and anions, they must be of a certain ratio. This is not true. Yeah. Okay, so let me just reiterate this. This is not true. It is only true if you attempt to, let's say, dissolve silver bromate salt in pure water. Then yes, silver plus and bromate concentration will be the same. Essentially the concentration is actually the square root of 3.39 times 10 to the power minus 5. Yeah. However, right, if let's say the solution already have a known concentration of silver plus or a known concentration of bromates, yeah, I can also introduce some silver plus or bromate respectively to the solution, and precipitation will still occur, and then both of them will be able to maintain a separate equilibrium concentration of the respective ions. Okay, so you need to be aware of this, and later on you'll be introduced the idea of common ion effect, and having this understanding is very important for you to appreciate this. Okay, yeah. So if you are not sure what I'm talking about, maybe I can just do a simple calculation for you over here. Okay, so the simple calculation I'm going to do for you over here will rely on the information which I have gotten above. Okay, or is directly in your lecture notes, so I do not have any extra information. Yeah. So again, let's say we attempt to dissolve silver bromate in pure water, in this case deionized water. Okay, then now we attempt to find out its solubility. Okay, so this is equals plus, let's say, BrO3 minus aqueous. Okay, so this is in pure water. Okay, so you assume that the solubility in pure water is A and A. Okay, and you know that the Ksp value is fixed. It is fixed at 3.39 times 10 to the power minus 5 mole squared dm minus 6. Yeah, so in this case, we can easily calculate A. I'm not sure whether you agree with me on that. Yeah, because from here, right, we can easily determine the Ksp to be concentration of silver plus to the power 1 and concentration of bromate to the power 1, and this is essentially A squared. And A squared is equals to 3.39 times 10 to the power minus 5. Okay, so in order to calculate A, we just take the square root of 3.39 times 10 to the power minus 5. So I'm going to just punch in the number in my calculator. So I'm going to get A is 5.82 times 10 to the power minus 3 moles per dm cube. Yes. Okay, so this will be the value A will be what we call the solubility of silver bromate in 1 dm cube of pure water. Okay, but does it mean that the value of silver plus and bromate in aqueous solution must only take this value? Let's say, does it mean that it can only take 5.82 times 10 to the power minus 3? The answer is no. It need not just take this value. It can take, in fact, I can have an infinite combination. Okay, so let me give you an example. So for example, let's say my solutions already have, okay, so let me just maybe just box up this area so that you'll be clearer. So we are looking at another scenario. So let's say my solution already have, let's say, 0.10 moles per dm cube of bromate. So for example, okay, and then I attempt to dissolve some silver bromate in the solution. So let's say the new solubility, we call it Y. So when Y amount of silver bromate dissolves, the amount of bromate will increase by Y, so plus Y, and then the amount of silver plus will go up by Y as well. So from 0 to Y. You'll be thinking, how come bromate, there's a 0.10 plus Y? Yeah, that's because I imposed a condition earlier on. If you can remember, I said that my aqueous solution already contains 0.10 moles per dm cube of bromate. Yeah, so in that case, if I attempt to dissolve silver bromate again, I will expect less to be dissolved, right? So let's say the solubility is Y. Let's say Y amount of silver bromate dissolved, then the amount of silver plus will go up from 0 to Y. The amount of bromate will go up from 0.10 to 0.10 plus Y. Okay, then when I attempt to write out the Ksp again, it's the same expression we are looking at, we are still looking at silver plus and then bromate over here, and then when we multiply the two together, you get Y brackets 0.10 plus Y, and then this is actually equals to the same Ksp, which is 3.39 times 10 to the power minus 5. Yeah, then from here we can solve for Y. Of course, to solve for Y, we need to do an approximation. We need to assume that Y is a very, very small number. So therefore, because 0.10 is way greater than Y, we will do an approximation. So therefore, this whole expression becomes 0.10Y equals to 3.39 times 10 to the power minus 5. So therefore, Y is actually equals to 3.39 times 10 to the power minus 4 moles per dm cube. Now, people, did you realize one thing? I have already created a second combination of silver plus and bromates. That is 3.39 times 10 to the power minus 4 and 0.1 together. When I multiply the two together, I will get Ksp. Yeah, so in that sense, I can have an infinite combination of silver plus, equilibrium concentration, and the relevance bromates equilibrium concentration. I combine the two. As long as it equals to Ksp, that will represent the maximum amount of the salts which can dissolve at 25 degrees Celsius. Okay, so please do not have the misconception that the amount of salt dissolved must be fixed at a certain ratio. It is correct. The ratio is correct if you dissolve it in pure water without the interference of other ions. Yeah, but if you have other ions coming into the picture, then it's a completely different story. Yeah. Okay, so I hope you don't find this too long-winded, but I think it's necessary to have to explain it in order to have a good understanding. Okay, so next we move on to the fourth section, which is on the difference between solubility and solubility products. Yeah, so basically you can obtain solubility from solubility products and vice versa. Yeah, I'm not sure if this flow chart helps you to understand. So basically, the solubility of a compound in grams per dm cube can be expressed in moles per dm cube. Okay, and the amount of ions dissolved that represent the molar concentration of the respective ions, and when you combine them, it's what we call the Ksp. I mean, combine them raised to the appropriate power that is. Okay, and then from Ksp, you can find out the molar concentration of the ions as well. And then after that, you can work backwards to find out the solubility of the compounds in moles per dm cube and grams per dm cube. Okay, but do take note that they are different things. So solubility and solubility products are actually different concepts. Yeah, they're not the same thing. So solubility product is fixed. It's a fixed equilibrium constant at a fixed temperature. And the saturated solution, okay, can have aqueous ions with an infinite combination, which I think I've painstakingly tried to explain to you earlier on. So using silver bromide as an example, so I can have infinite combination. But solubility of a compound, right, in terms of moles per dm cube or grams per dm cube, is actually a fixed number, okay, at a given temperature. And usually we express solubility in either grams or moles per dm cube of that solvent. Yeah, so that is the difference. Okay, so one is finding out how much of the salt can dissolve. The other one is an equilibrium constant involving the concentration of the aqueous ions. Okay, so if that's okay, then we'll look at exercise 4.1. You are given the solubility of silver chloride. Take note, it's silver chloride solubility. Okay, taken to be 1.46 times 10 to the power minus 3 grams per dm cube at 18 degrees Celsius. So you are being asked what is the solubility product of silver chloride at this particular temperature. So this should be a relatively straightforward question. I think the first thing we need to do is we need to convert this to moles per dm cube. So in this case, solubility of AgCl in moles per dm cube will be 1.46 times 10 to the power minus 3 divided by 143.5. Okay, and then from here you will be able to get 1.0174 times 10 to the power minus 5 moles per dm cube. Okay, and then to determine Ksp, in this case, the Ksp of silver chloride will be the concentration of the silver plus and the concentration of chlorides. And because they dissolve in a 1:1 ratio, so I'm expecting the two numbers to be the same. So so that will be 1.0174 times 10 to the power minus 5. In this case, squared. Okay, or if you're not comfortable, I mean, let's say you prefer to just write everything out, that's fine also. Yeah, just write everything out times 10 to the power minus 5, and then you punch your calculator, you should be able to get 1.04 times 10 to the power minus 10 mole squared dm minus 6. Okay, always remember to write out the units. This is something which your seniors often forget. Okay, or students often forget. Okay, so next we'll look at exercise 4.2. So we have a suspension of solid magnesium hydroxide in water. So it's known as milk of magnesia. It alleviates minor stomach disorder by neutralizing stomach acid. So the hydroxide concentration is too low to harm the mouth and throat, but the suspension dissolves in the acid stomach juice because you expect some sort of acid-base reaction. Okay, so now you are asked to find the solubility of magnesium hydroxide in moles per dm cube and grams per dm cube, given the Ksp of magnesium hydroxide to be 6.30 times 10 to the power of minus 10. Okay, so one simple way to do this is actually simply to write out the equation. So magnesium hydroxide solid equilibrates to give you Mg2 plus aqueous plus 2OH minus aqueous. Okay, so let's say A amount of magnesium hydroxide dissolves. So therefore the concentration of Mg2 plus at equilibrium will be A, and then OH minus will be 2A. Okay, so this is the concentration at equilibrium. Okay, in terms of moles per dm cube. Okay, and then right now we'll write out the Ksp expression. So Ksp is equals to the concentration of Mg2 plus raised to the power of 1, and then concentration of OH minus raised to the power of 2, and then this is equals to A multiplied by 2A squared. Okay, and then this is actually equals to 4A cubed. And since you are given the Ksp value to be 6.30 times 10 to the power minus 10, so therefore 6.30 times 10 to the power minus 10 is equals to 4A cubed. You can easily determine A to be 5.40 times 10 to the power minus 4 moles per dm cube. Okay, so this is solubility in terms of moles per dm cube. So now we'll need to convert to grams per dm cube because you are given the MR, and of course you are told to give the solubility in both moles per dm cube and grams per dm cube. So therefore solubility in terms of grams per dm cube will then be equals to 5.40 times 10 to the power minus 4 multiplied by 58.3. Okay, so you are going to get 0.0315 grams per dm cube. Yep, and yeah, this is how we solve solubility simple calculation involving solubility equilibrium. I hope it's not too daunting for you. Okay, then so next we have a planning icon over here. So in order to determine the solubility products of a sparingly soluble compound, usually you'll be asked to write out maybe a simple plan. It's actually not too difficult to write out this particular plan if you have the big picture in mind. So in short, you are attempting to dissolve as much as possible of the salts in water. Okay, so that means you are supposed to prepare a saturated solution, in this case at room temperature. Yeah, so normally what you'll do is you will just attempt to mix the salts and water together, and then you might just want to have a cork or you try to mix it in a conical flask, and then you have a cork or a stopper, put it at the mouth of the conical flask, and then you swirl it or you shake it real hard, and then make sure that they are undissolved solid, of course. I mean you don't want to add the salt and then everything dissolve and then you keep swirling. Okay, so just make sure they are undissolved solids. So you swirl it really hard and then you leave it there for equilibrium to be established. Ensure that you leave it there for some time. So usually you will take about 5 to 10 minutes, but it really depends. If you're writing the planning yourself, just make sure you mention that you leave it to stand for a while. Let's say 5 to 10 minutes. If you're not writing the planning, you just read the instructions given to you and just perform accordingly. Okay, and then do take note of the temperature of the surrounding as well. So if it's room temperature, just take note of the room temperature at that point in time. So for Singapore's weather, it can range between 25 degrees Celsius to about 30, 33 to 32, so it really depends. Okay, if it needs to be maintained at a water bath, so just make sure that you have a water bath uh, which can control the temperature thermostatically. And then if you want to investigate the common ion effects, which later will introduce you to section 6.1, then of course you can refer to that later on, but you might want to prepare a different initial concentration of the common ion. Okay, so that will be this particular bullet point. Okay, and then of course you need to filter off the undissolved solids. That is very important. So you have a rough planning over here. Yeah, and make sure that when you filter them off, you use a dry filter funnel and a dry filter paper. Okay, the word dry is very important over here because you don't want to unknowingly dilute your saturated solution. Yeah, and then in order to determine the amount dissolved, the ions dissolved, then usually we will either perform titration if let's say it contains hydroxide, or maybe we can even perform a redox experiment. So for example, if it's bromide in this case, we could potentially add in excess iodide, and then iodine is produced, and then we just titrate iodine with sulfate, something along those lines. Yeah. So when it comes to planning, I think you will encounter it a little bit more in JC2. So just be aware of how you should or how you could write a generic procedure, uh, which is actually quite important in your learning. Okay, yeah. We'll move on to ionic products, which is actually a similar concept to reaction quotient. Okay, so in this case, the ionic product of a sparingly soluble salts is the product of the molar concentration of the constituent ions in the solution raised to the appropriate power. So basically, the solution is not a saturated solution. So basically, you just dump two things in together, and then whatever concentration you get, that will be the ionic product. Okay, so maybe we can just move back a little bit to this. Okay, so let's say in our case here, right, you can actually calculate the ionic products. So, but of course, you need to do some scaling. So you notice that over here, right, the phrasing is different initial constant volumes of these two were added to 200 cubic centimeters of distilled water. So from here, you need to calculate the number of moles of silver plus. So you just scale it to 40. And then after that, they are present in a total volume of 250. And then you scale it to 250, and then you are able to find out the initial concentration of silver plus. And then from the bromates over here, you can also find out the initial concentration of bromates. Yeah, so at that point in time, that particular initial concentration before precipitation occur, we call that the ionic product if you multiply them together. Okay, so basically you can multiply them together in the same fashion, except that the concentration of silver plus aqueous and the concentration of bromide, they are not at equilibrium. They are just the initial concentration. Yeah, yeah. So you need to understand the concept of ionic products. Yeah. So ionic product of silver chloride is basically given at same expression. So it can take on any value. Okay. But what is the significance of this value? Yeah. So the significance is that if the ionic product takes on the same value as Ksp, yeah, then what you're getting in is actually a saturated solution. If the ionic product takes on a greater value than Ksp, then you expect some of the excess ions to be precipitated out as the insoluble salts. Yeah. So you can just imagine this way, because if the ionic product is greater than the Ksp, that means that the solution contains more ions that it can hold. So the rest, they must force it out of the solution as the insoluble salts. And that is where you get ionic product equals to Ksp, where equilibrium is re-established, so called. So when that happens, then precipitation was stopped. Yeah, so ionic product gives you an indication of whether precipitation will take place. So if ionic product's value is greater than Ksp, precipitation will occur. If it's lesser than Ksp, then there will not be any precipitation. Okay, so I hope you can appreciate this understanding. If we have an exercise 5.1, so we have a certain concentration of calcium 2 plus mixed with equal volume of sulfate. So equal volume here actually means that the concentration will halved. Okay, so we don't really need to know the volume. As long as we know that it's equal volume, we know that concentration will half. So the question is, no precipitation of calcium sulfate occurs. They ask you to calculate the ionic product in this case. Yeah, so essentially the ionic product is concentration of calcium 2 plus. Also, maybe I should write this out first. Calcium 2 plus concentration, and then concentration of sulfate. Okay, and then this is equals to concentration should half, so I should be getting 5.00 times 10 to the power of minus 4. Okay, and then 5.00 times 10 to the power of minus 4. Okay, and then I combine the value, I'm going to get 2.50 times 10 to the power of minus 7 moles squared dm minus 6. Yeah, so no precipitation occurs. So this is the ionic product. If you are interested in the solubility products, you can just Google it. Okay, so we have checked it out for you. So the Ksp of calcium sulfate, if you Google it, is actually 4.93 times 10 to the power minus 5. So you notice that this value is less than Ksp. So therefore, no precipitation occurs. Okay, so I think earlier on I have touched on section 5.1. So the second bullet point. So if ionic product is less than Ksp, precipitation will not occur. If ionic product is greater than Ksp, then precipitation will occur until IP equals Ksp. Okay, so you might want to take note of this. When this is greater than Ksp, so precipitation occurs until IP equals to Ksp. Yeah. Okay, so ionic product allows us to predict if precipitation will occur when two solutions are mixed. Okay, yeah. So let's move on. Consider the sparingly soluble salt barium sulfate. Okay, so adding solid barium sulfate in small amount to pure water. When does the solution become saturated? So will there be precipitation? Okay, so we have two columns here. So the middle column is telling us when I'm just adding the solid to pure water. Okay, so IP equal Ksp lah. So that's the context. So when I mix the aqueous solution together, so the question is, will there be precipitation? Yeah, when I dissolve the solid, I think what I'm interested in is whether the solution will be saturated or not saturated. Okay, so if the ionic product is less than Ksp, so in this case, I think it's pretty straightforward. I won't get precipitation. Okay, yeah, I think I'll just look at the rightmost column first. If ionic product is equals to Ksp, that's an equilibrium. You will see the first trace of precipitate just appears. So it's like the precipitate wants to come out but not able to come out, or about to appear. Okay, so these are the two terms you can use. The precipitate about to appear, or the first trace of PBT appears. Okay, if ionic product is greater than Ksp, then precipitation will occur until IP equals to Ksp. Okay, then if you are looking at adding barium sulfate into pure water, right? Actually, this is not very significant, but if you want to look at the concept of ionic product, so basically the solution is not saturated because you can keep dissolving barium sulfate. Okay, but if the solution is already saturated, then you are not expecting any amounts or any more solid barium sulfate to dissolve. Yeah, if you try to dissolve more, nothing can dissolve. Yeah, because the maximum amount of aqueous ions, in this case Ba2 plus and sulfate, is already fixed by the Ksp. So even if you force it to dissolve, it cannot dissolve unless you heat it. But if you heat it, it's a different ball game because you are changing the value of Ksp. Okay, then yeah, if that's okay, we'll move on to exercise 5.2. So for exercise 5.2, you are asked, will a precipitate form when I mix 0.1 moles per dm cube of a certain concentration of lead nitrates to sodium sulfates, again a certain fixed concentration as well. Are you given a volume here? No, you're not given volume. Okay, but it doesn't really matter because oh, okay, sorry, yeah, given volume. I missed that. So yeah, the volume is actually let me just highlight in purple. So yeah, adding 100 dm cube, that's 100 cubic centimeters, and 0.4 dm cubes. Okay, so I think the question they ask is, will there be a precipitate being formed? So that's actually a pretty straightforward question. So all you need to do is to sum up the total volume. Okay, so what is the total volume? So in this case, so let's try to do it in the empty space here. So the total volume, okay, is actually 0.500 dm cube. Okay, then I'm going to calculate the concentration of lead 2 plus, not at equilibrium, but when I mix the two solutions together. Okay, so that will actually be equals to 3.00 times 10 to the power minus 3. Okay, so take note that this is 1:2 ratio, but we don't care about nitrates because nitrate is not involved in the precipitation. Yeah, so the concentration of lead 2 for a solution 3.00 times 10 to the power minus 3 will be 3.00 times 10 to the power minus 3. Okay, then I need to scale it to 0.100 because this is the volume being added. All right, and then at the same time, I also need to divide by the new volume, which is 0.500. Okay, so with this, I'm going to get 6.00 times 10 to the power of minus 4 moles per dm cube. Okay, so I'll do the same thing to sulfates. So for sulfate, it will be 5.00 times 10 to the power minus 3. Then I will find out the number of moles from the volume. And then I will scale it to 500 because that's new volume. And then from here, I'm going to get 4.00 times 10 to the power of minus 3 moles per dm cube. Okay, then from here, I will attempt to calculate the ionic product. So the ionic product of lead sulfates will then be equals to the concentration of lead 2 plus at that point in time multiplied by the concentration of sulfates, and this will be 6.00 times 10 to the power minus 4 multiplied by 4.00 times 10 to the power minus 3. And then you notice that when you punch your calculator, you're going to get 2.40 times 10 to the power minus 6 moles squared dm minus 6. And you notice that this value is actually bigger than the Ksp. Okay, so this is actually bigger than Ksp. So therefore, I expect precipitation to occur. Okay, so expect precipitation of white PPT to occur. Okay, so I hope you find that it's actually pretty straightforward in terms of calculation, so it's not as difficult as what you might be thinking. Okay, then yeah, if that's okay, we will move on to do exercise 5.3, but before that, I'll just erase all this so that it's not really necessary to input all this in. Yeah. Okay, so I'll just erase everything. Okay, so for exercise 5.3, we have calcium nitrate is added to 2.0 0.00 times 10 to the power minus 4 moles per dm cube of magnesium sulfate. So what is the minimum concentration of calcium 2 plus before a precipitate of calcium sulfate can be formed? So this is this question is positioned in a slightly different way, because now we are given the Ksp, right? Yeah. So in that case, right, if you notice, there is actually an infinite combination of Ca2 plus and sulfate which can be equated to the Ksp. Yeah. So since I'm already given a certain concentration of sulfates, this is already given, right? Okay. So what I need here would be a minimum calcium 2 plus concentration that I need to add it in order for this value to be equals to the Ksp, which is 2.40 times 10 to the power minus 5. Okay, and because the sulfate concentration is already known to me, which is 2.00 times 10 to the power minus 4. So all I need to do is just to shift this thing over. So I'm going to get calcium 2 plus minimum. Okay, and this is simply equals to 2.40 times 10 to the power minus 5 divided by 2.00 times 10 to the power minus 4. And then from here, I'm going to get 0.120 moles per dm cube. Yeah, so this is simply the concentration of calcium 2 plus in that solution. Okay, in that solution, in the combined solution, that I need the minimum concentration before I can form the first trace of calcium sulfate precipitate. Okay, so this is what the question is actually asking of you, not the concentration of calcium before I add them together. Yeah, you notice that or if there is one, the tutorial question, there's one tutorial question that actually asks you something along those lines, like the concentration before you add and after you add. So the value is actually a little bit different. Yeah, if everything is okay, we'll move on to 5.2, which is on selective precipitation. So what this actually means is that I have two metal cations together, then I just want to precipitate one out but not the other. So it's called selective precipitation. Okay, so ideally the solubility of both must differ by quite a bit, because if they are quite similar, then it's very difficult to separate one almost entirely from the other. Okay, so we'll look at exercise 5.4 to help us understand what exactly is going on for this. So in a solution, I have silver plus concentration 1.0 times 10 to the power of minus 2, and then let 2.0 times 10 to the power minus 2, so it's given to you. Sodium chloride is added to this solution. You'll notice that if a question just want to make it a bit easier and let the students focus in practicing calculation just for at the beginning stage of learning, right? Usually they will add solid in instead of a solution. The reason is when you add solution, you are actually diluting the concentration of the respective cations as well. So they just want to make the calculation easy for you. Yeah. So in most cases, please take note that whether you are adding solid or you are actually adding solution. Yeah. So it does make the calculation a little bit different. Yeah. I mean, you can try to calculate if I'm adding solution in, but it's actually way harder, or a little bit harder. Yeah. Okay. So you're given a Ksp of silver chloride and lead chloride. So the value is 1.80 times 10 to the power minus 10 and 1.60 times 10 to the power of minus 5. Yeah. So you'll notice that the first part of the question is asking you what is the minimum chloride concentration necessary for each salt to be precipitated out. So to position the question in a slightly different way, right? Actually, they are asking you which salt is more insoluble. Yeah. Then sometimes students will straight away just look at the Ksp value and then make a conclusion from there. It's actually quite dangerous, because if you attempt to write out the Ksp expression, right, you realize that because the cation and anion ratio are different, right? Looking at the value itself may be a bit misleading, and then at the same time, in our case here, the concentration of silver and lead-2 are also a bit different. Okay, so it is best to perform calculation. If not, we just follow the flow of the question. Usually the flow of the question it serves as a guide to how we should go and perform our necessary calculations. Okay, so I think it does help if we can write out a Ksp expression for silver chloride in this case, so as to remind us how it looks like. And then of course for lead chloride as well, so Pb2 plus and then Cl minus squared. Okay, and then since you are told that the concentration of silver plus is 1.00 times 10 to the power minus 2, so therefore you can straight away calculate the minimum chloride for silver chloride to precipitate out. Okay, which is equals to the Ksp, which is 1.80 times 10 to the power minus 10, divide by 1.00 times 10 to the power minus 2. Okay, so you will get 1.80 times 10 to the power minus 8 moles per dm cube. Okay, and then using the same logic, the minimum amount of chloride for lead chloride to precipitate out. Okay, so this is actually equals to the Ksp, which is 1.60 times 10 to the power minus 5. Okay, divide by concentration of lead-2, which is 2.00 times 10 to the power minus 2. And then you need to square root the whole thing, because remember that this is squared. Yes, and then from here you can calculate this to be 2.83 times 10 to the power minus 2 moles per dm cube. So if you simply just look at the power is raised to, you straight away notice that silver chloride is actually easier to be precipitated out as compared to lead chloride. So in this case, the next question is asking you which salt precipitate out first. So of course the obvious answer is silver chloride. So how can silver plus be separated from lead-2 plus? And then find the percentage silver plus left in the solution. And then now they ask you, is the separation effective? Yeah. So in this case, you know that the concentration of chloride in the solution before lead chloride is being precipitated out, right, is actually 2.83 times 10 to the power minus 2. So therefore, I will add sodium chloride until just before 2.83 times 10 to the power minus 2. Does that make sense to you? Yeah, so I will just need to, of course I need to do the calculation beforehand. I need to like calculate, what is the mass corresponding to this number of moles, and then maybe account for some errors like 2 or 3% error. Maybe some of the sodium chloride is being stuck somewhere. But other than that, taking all these factors into consideration, yeah, I will need to add slightly less than 2.83 times 10 to the power minus 2 in order to precipitate out as much silver chloride as I can. And then after that, I will then filter off the silver chloride, and then whatever remains in the solution is actually lead-2 plus. Okay, so remember that if I'm going to introduce 2.83 times 10 to the power minus 2 moles per dm of chloride, that is the point where lead chloride just about to precipitate out. Okay, then if you take this value, which is 2.83, 2.83 times 10 to the power minus 2, and then you multiply it with silver plus, and then you equate it to the Ksp of silver chloride. You will notice that what you are calculating here, right, is actually the concentration of silver plus that remain in the solution. Okay, so if you punch your calculator, you should be getting 6.36 times 10 to the power of minus 9. Okay, moles per dm cube. Yeah, so this is also telling you that it is impossible to 100% separate everything out. There will still be a small amount that remains dissolved. Okay, and then you take this value, okay, divide by the original concentration, which is this, times 100%, you will be able to find out the percentage of silver plus remaining in the solution. So the percentage of silver plus remaining in the solution, okay, is actually equals to 6.36 times 10 to the power minus 9 divides by 1.00 times 10 to the power minus 2 times 100%. So I'm going to get 6.36 times 10 to the power of minus 5%. Yeah, and this is an excellent separation because it's close to 100%. Yeah, okay. So I hope the calculation has shown you several ways or several kinds of questions which could potentially be asked of you when you're dealing with KSP. Okay, so now we are moving on to the last section, which is some students felt that it's harder. Depends, but if you have a good understanding of chemical equilibrium, this particular section is actually not so difficult. It's actually on the common ion effect and the rest of the factors affecting solubility. Okay, so now we consider a mixture of calcium fluoride and its aqueous ions in a saturated solution. So let's say I begin my solution with either calcium 2 plus or fluoride. Then according to Le Chatillon's principle, I expect the presence of either ions to suppress the dissolution of calcium fluoride, because you expect the position equilibrium to lie more to the left as compared to pure water. Yeah, so that's the main idea of this big name known as the common ion effect. But I think I've mentioned maybe in the tutorials that the common ion effect term cannot be used as an explanation. But what can be used is actually using Le Chatillon's principle and talking about how position of equilibrium will shift. Okay, yeah. So we'll just do a simple exercise 6.1. So you are given the Ksp of silver chloride to be 2.0 times 10 to the power minus 10. So again, let us try to write out a Ksp expression for silver chloride. So that will be silver plus and chloride. Okay, so I will equate this to 2.00 times 10 to the power minus 10. So in pure water, if A amount dissolves, so in this case I'm going to get A squared equals to 2.00 times 10 to the power minus 10. So the solubility of silver chloride will then be 1.40 times 10 to the power minus 5 moles per dm cube. Yeah, so this is the solubility of silver chloride. Okay, so now you are expected to calculate the solubility of silver chloride in 0.1 moles per dm cube of sodium chloride. Yeah, so we'll perform the same calculations using what I've shown you at the start, if you can remember. So again, we will write out an equilibrium expression of silver chloride in this way, and then assuming that at the beginning we already have a fixed concentration of chloride, which is what we were told, and this is actually 0.100. And in this case, let's let the new solubility of silver chloride to be Y, for example. So in this case, silver plus will have Y amount, and then chloride will be 0.100 plus Y. Okay, then in this case, the Ksp expression will now be Y multiplied by 0.100 plus Y equals to 2.00 times 10 to the power minus 10. And because Y is a much smaller number than 0.100, so I expect this whole expression to be simplified to this 2.00 times 10 to the power minus 10. And then Y is therefore equals to 2.00 times 10 to the power minus 9 moles per dm cube. You realize that the solubility of silver chloride reduced quite drastically by about 10,000 times. Okay, from 1.40 times 10 to the power minus 5, it reduced to 2.0 times 10 to the power minus 9. Okay, so how do we normally explain this? We will say that the presence of chloride which is actually the common ion, suppresses the dissolution of silver chloride. Okay, yep. Okay, so some comments on the data. I think the first bullet point I've already mentioned to you. So when you dissolve pure salt in water, the concentration of the ions is determined by the stoichiometric ratio of the cations and anions. So for example, if you are dissolving silver chloride, you expect the concentration of the ions in a saturated solution to be 1:1. If you dissolve calcium sulfate, for example, you expect it to be 1:1 as well. But if you dissolve, say, lead chloride, so it will be 1:2. Okay, and from the above, you notice that the solubility of silver chloride actually reduces from 2.00 times 10 to the power minus 9 reduces from 1.40 times 10 to the power minus 5 to 2.0 times 10 to the power minus 9. So, so the presence of chloride as the common ion actually suppresses the dissolution of silver chloride in the solution. And then from here, from the earlier example, we also teach you how to go about performing the calculations. Okay. Next, we're going to go into section 6.2, which is on the formation of complex ions. So, for example, in the case of adding sodium hydroxide to Al3+, in the beginning, you expect the formation of the white PBT of aluminum hydroxide. So, so you expect maybe an equation at the beginning to be like this: Al3 plus 3OH minus, and then arrow AlOH3 solids. Yeah, so the precipitation will keep occurring until you get almost the maximum amount of Al3 plus, which you can precipitate out from the solution. And then after that, there will be a small amount of Al3 plus and OH minus maintained by virtue of the Ksp value. Okay. However, when you add excess OH minus, you notice that the white PBT dissolves to form a colorless solution. So this colorless solution is actually this complex known as aluminate. So why is that the case? Why is it that aluminate, the formation of aluminate will encourage the formation or the dissolution of aluminum hydroxide? Okay, so the idea is actually quite straightforward. In a limited amount of hydroxide, you will always form aluminum hydroxide. But in excess hydroxide, the formation of aluminate is actually preferred. In this case, a simple explanation will be Al3 plus is actually a very good Lewis acid, having a high charge density, a very strong Lewis acidic center. So it has a very strong tendency to attract a strong Lewis base such as OH minus. So the formation of aluminate is actually a preferred reaction, but at any one point in time when you add in OH minus, the hydroxide is always in limited amount, so aluminate will never be formed. So aluminate will only be formed when you already precipitate out the maximum amount of aluminum hydroxide. Yeah, so in that case, when you add in excess OH minus, the excess OH minus actually reacted with the little bit amount of Al3 plus that is present in the solutions. So this little bit amount of Al3 plus that is present in the solution, right, will result in equilibrium 2 operating. And it is analogous to removing Al3 plus from the first equilibrium. Yeah, so when Al3 plus is being removed from the first equilibrium, it will encourage the POE, the position of equilibrium of 1, to shift right. Okay, therefore increasing its solubility. Yeah. So in that case, you can argue that the presence of excess OH minus leading to the formation of a complex encourages the solubility of the sparingly soluble aluminum hydroxide. Okay, yep. Then, okay, so we have example 2. When I add silver nitrate to a solution containing halite, I will first form precipitate of silver chloride. I mean, in this case, if I have chloride, I will form silver chloride. silver bromide, which is cream, and then silver iodide. Yeah. Then if I introduce aqueous ammonia, what's going to happen? So silver chloride will actually dissolve in excess aqueous ammonia to give a color solution, and you should be able at this stage to predict that maybe it is due to the formation of a complex. Okay, and then for silver bromide, partially soluble in dilute ammonia, but soluble in concentrated ammonia. Okay, for silver iodide, insoluble in both. Yeah, so this particular data is actually in your data booklet. It should be in the second last page, the page before the periodic table. So please go and take a look. And you notice that this has got to do with the value of Ksp as well. The value of the Ksp value for silver iodide is in the region of 10 to the power minus 17, but that of silver chloride is in the region of 10 to the power minus 10. So the bromide is actually in between. Okay, so the explanation can be found here. You will be able to understand this a little bit better when after you have done transition metal or after we have gone through some of the QA lab. But in general, this is what happens. So when you add in when you add silver nitrate to halide, you actually form similar to what I've done above. So initially, we are actually talking about the formation of the halides, so the insoluble halides. And then when the maximum amount of halide is being formed, it is able to maintain a small amount of silver plus and a small amount of X minus by virtue of its Ksp. However, when I add in aqueous ammonia, ammonia actually forms a complex, which is what we call diamine silver 1 complex. So this is known as a diamine silver 1 complex. And this complex is soluble in water. And the formation of this complex actually involves reacting the small amounts of silver plus being maintained by the Ksp of silver X. Yeah, so similar case as aluminium hydroxide. So when equilibrium 2 operates, POE of 1 will shift to the right. Okay, and then when POE of 1 shift to the right, silver plus concentration decreased. Or you can say that the value of ionic product starts to decrease. I mean, however you call it, and then the decrease in silver plus will cause the position of equilibrium of 1 to shift right, which is what I mentioned, increases the solubility of silver halide. Okay, so so this will occur until ionic product is less than or equals to Ksp lah. Okay, now however, whether the salts can dissolve in excess ammonia or not is actually dependent on the Ksp value. Okay, yeah, so if you look at the explanation for silver chloride, it reads the precipitate is able to dissolve completely for silver chloride because the addition of dilute ammonia is sufficient to lower the concentration of silver plus such that the ionic product becomes smaller than the Ksp. Yeah, however, for the case of silver bromides and silver iodides, right, the addition of dilute ammonia is not sufficient, okay, to lower the concentration of silver plus. Yeah, so therefore the precipitate will continue to remain undissolved. Okay, so I think you might want to take note of this explanation because it will help you a lot in your QA as well as your theory. Okay, then okay, so we'll move on to exercise 6.2. I think you should be able to read this on your own. Okay, so for exercise 6.2, you are asked to explain why the solubility of lead chloride decreases in dilute hydrochloric acid but increases in concentrated hydrochloric acid. Okay, so I think it's the same issue. In dilute hydrochloric acid, we are having a common ion, which is chloride. Okay, so maybe let me write the equation out. PbCl2 solid equilibrates with Pb2 plus aqueous plus 2Cl minus aqueous. Okay, so the presence of dilute HCl, right, it's similar to the common ion effect which we discussed earlier on. So it will suppress the dissolution of lead to chloride. Okay, however, right, in concentrated HCl, another equilibrium is taking place. So in the presence of concentrated HCl, right, we are actually looking at the formation of this particular complex. Okay, Pb2 plus equals plus 4Cl minus equals. So it will lead to the formation of PbCl4 2 minus equals. Yeah, so the formation of this complex, okay, because it's high, so you expect this complex formation to take on a very high Kc value. Okay, so the formation of this particular complex, which is called dichloro-lead-2 complex, will actually remove lead-2 from the dissolution of lead-2 chloride. Yeah, so because it's being removed, because lead-2 plus is being removed from the first equilibrium, yeah, it will encourage lead-2 chloride equilibrium position to shift to the right. So encourage it to be more soluble. Yeah, so the explanation is actually similar to what you have earlier on. Okay, so I repeat, the formation of this highly soluble complex, okay, by excess chloride in the presence of concentrated hydrochloric acid, okay, will cause the position of equilibrium of 1 to shift to the right because it is disturbing, or it is analogous to removing lead-2 from equilibrium 1. So removing lead-2 plus from equilibrium 1 will cause the POE of 1 to shift to the right. So POE of 1 shifting to the right is analogous to lead chloride being more soluble, okay, in the presence of concentrated hydrochloric acid. Yeah, so all this will lead to the formation of the complex PbCl4 2 minus. Yeah, and then the effects of pH is actually quite an interesting story. You will be more familiar when you are dealing with acid-base equilibrium, okay, which is in our next topic, topic 14, I believe. Okay, but before that, maybe we want to give you some introduction. What exactly is pH and pOH in the mathematical sense. So pH is actually the negative log to the base 10 of concentration of H plus. pOH is actually the negative log to the base 10 concentration of OH minus. At at 25 degrees Celsius, this is an expression which you need to know. pOH plus pH equals to 14. Yeah, so if you wish to know more, please read up on the topic on acid-base equilibrium, or you can revisit it in JC2. Yeah, so for our examples here on magnesium hydroxide dissolving in aqueous solution, so the presence of a strong Bronsted acid such as HCl, right, will neutralize the OH minus form, so it will encourage magnesium hydroxide to dissolve. Okay, so the solubility of magnesium hydroxide will increases when the pH of the solution decreases, or you can say that it will decreases when the pH increases. Okay, yeah, so from here you can actually work on exercise 6.3. So you are given the pH of a saturated solution of magnesium hydroxide to be 10.52. So if you wish to, you can easily do a conversion. So if the pH is 10.52, you know that pH plus pOH is equals to 14. So therefore, you can easily calculate pOH from here. So the pOH will be 3.48. So therefore, the concentration of OH minus will be 10 to the power of negative 3.48 moles per dm cube. And then from here, I can easily calculate the solubility of magnesium hydroxide at pH 10.52. Okay, how do I do that? Basically, I just put in Mg2 plus, and then I just put in 10 to the power minus 3.48. I will equate it to the Ksp, which is given to be 1.80 times 10 to the power minus 11. Okay, sorry, I need to square this because it's MgOH2. Okay, so from here I can calculate the concentration of Mg2 plus. I believe it should be 1.64 times 10 to the power minus 4 moles per dm cube. Okay, now if I'm going to and then for part 2, right, you're asked to calculate the solubility of magnesium hydroxide if the saturated solution 1 is mixed with a solution maintained at pH 9. Okay, so now if I'm going to maintain the solution at pH 9, what I'm going to do now is I'm going to calculate the pOH again. So the pOH will be 10 to the power minus, the pOH will be 5, because that will be 14 minus 9 equals to 5. And then the concentration of OH minus will be 10 to the power minus 5 as well, 0.00 if you want to. And then I'm going to do the same thing, Mg2 plus multiply by 10 to the power minus 5.00 squared, and this is equals to 1.80 times 10 to the power minus 11. So the concentration of Mg2 plus, I can easily calculate. It will be 0.180 moles per dm cube. So you notice that as the concentration, as the pH decreases from 10.52 to 9.00, the solubility of magnesium hydroxide increases from 1.64 times 10 to the power minus 4 to 0.180 times 10, 0.180 moles per dm cube. Okay, yep. And then I hope everything's clear. It's not a very difficult topic, but I think it's best to study it together with chemical equilibrium. And yes, the final section you can read on your own. So it's application to real life. It's on daily life. Maybe you can read up on hot water. You don't really encounter this in Singapore, but usually in temperate countries with rich minerals. So you can read up about hot water if you want to. Kidney stone for health reasonings, if you want, you can read up on this as well. So those people with kidney stone should avoid certain food which is high in ethane diolate or oxalate. For example, spinach, peanuts, sweet potatoes. Okay, so if you're interested, you can read more about this as well. So looking ahead, again, my advice is before you move on to study to JC2, I think it's good for you to revisit chemical equilibrium, which in terms of Kc and Kp. Okay, and of course now you have learned Ksp, so you can lump them together in one family. Yeah, so these are all the equilibrium constants which you have studied so far. And please learn how to do some of the basic calculations, because if you move on to JC2, when you study acid-base equilibrium, it's likely to be a lot more challenging for you, simply by basing on the experience from your seniors. And of course, solubility products as a topic is very important to ensure that you have a good understanding. Please ensure that you have a good understanding of this topic in order to appreciate the QA experiments which you will be doing in JC2. Of course, having a good understanding of this will help you to improve your theory in trying to explain why you observe certain precipitate appearing and why certain precipitate actually dissolves. Okay, so with that, then yeah, so I'll wish everybody a happy holiday, and do expect more of such videos in next year. And yep, please do your revision and have a good rest.